clearly.
So, hello everyone. Today we have Professor Jaya Iyer from Institute of Mathematical Science, Chennai, and she will continue her talk on the Abelian variety. It's the first part of it. She spoke on the February 24. Now in this today she will continue the Abelian variety part 2. Professor Jaya Iyer, you can start.
Yes, I am very happy to give the second talk, and I really thank Devendra and all the organizers for really taking their time out. All these few months they have been organizing these talks, so it's really a pleasure to talk to all of you and also to meet Professor Ravi Kulkarni after a very long time. So it's nice seeing everyone, at least online. So actually, I would like to continue my talk, or rather discussing topics on abelian varieties. So let us recall briefly what we did last time in the first talk. So we introduced the definition and basic properties of abelian varieties, namely saying that it is a group variety and which is complete. And so we discussed certain rigidity theorems, and we looked at the structure of abelian varieties over the complex numbers. And so over complex numbers, so they have a very nice structure that is of a complex torus. So that means it looks like a complex space of say G dimension and modulo a complete lattice. And with the help of the topological structure of a complex torus, one can compute the cohomology of this torus by Pune formula. And then we wanted to understand the polarizations or line bundles on complex torus. So that is given by Riemann bilinear forms on the lattices, and which can be extended over the complex G-dimensional space, satisfying certain Riemann property. And so all this data, essentially the topological structure of your complex torus together with the Riemann bilinear form, it helps us to understand the structure of line bundles on complex torus. And basically we said that a line bundle on a complex torus is precisely given by a pair. So this is a Riemann form, so that is actually a skew symmetric form satisfying certain properties, and a semilinear character. So these two data determines a line bundle on a complex torus. So let me just show the slides quickly. So this is what we said is a abelian variety. So that means it is a group variety having a multiplication map, which is actually also a morphism of varieties, together with the inverse map, which is again a morphism of varieties together with a identity element. And then we want such a variety to be complete, and then we say it's an abelian variety. And then we had this rigidity theorem, which basically helps us to conclude that every morphism between two abelian varieties is the composite of a homomorphism. That means it's a group homomorphism together composed with a translation map. And it also helps us to prove that the group law is always commutative. And then using the exponential map, because any abelian variety over complex numbers is a compact connected complex Lie group, using the exponential map, we can conclude that the abelian variety looks like a complex torus, so which is a G-dimensional complex space modulo a lattice. So this a lattice is a maximal free abelian subgroup of your G-dimensional complex space. So here it is important to note that not every such quotient is an abelian variety whenever G is at least 2. So when G equals to 1, so that means you are just looking at your complex plane modulo a lattice generated by two independent elements. So that is actually an elliptic curve. So any such complex torus in dimension 1 is always an elliptic curve. So that means it has an algebraic structure and it can be embedded inside P2. But actually if G is bigger than 1, so that is no longer true. And so once we realize your complex torus as a product of circles, say you take 2G copies of your circle, So then by Punnett formula, we can compute the cohomology of such complex tori. And then essentially we can compute the dimension of your cohomology groups, that is the singular cohomology groups. And it also helps us to find the structure of the cohomology. So essentially, the cohomology is generated by the first cohomology of a complex torus. So that's what this last statement in the slide means. And so it also says that you can realize your Rth cohomology of your complex torus as the space of alternating R forms on the lattice with values in Z. So essentially, you can the cohomology structure and all just boils down to looking at the linear algebra on the lattice. So once we have that, we can try to understand the line bundles on such complex tori. So why this is essential is because if you want to understand the line bundles on any complex manifold, so essentially we just look at this exponential sequence given by the sheaf structure sheaf on your manifold. And so you have the exponential map and whose kernel is Z. So this is basically the map, and you take any holomorphic function and look at the corresponding image here, which is the e power f here. So that is going to be in the sheaf of nowhere vanishing space of sections on your manifold A. So such a sheaf sequence corresponds to an associated cohomology sequence. So this is given by H1, the first cohomology with coefficients in Z and coefficients in your structure sheaf OA, and in this multiplicative structure sheaf OA star and so on. And then it continues to the second cohomology group with coefficients in all these sheaves here. So here what we understand here is that if you look at the space of line bundles, so this is precisely given, denoted by Picard group of A. So this is precisely your first cohomology with coefficients in the multiplicative structure sheaf on your manifold A. So that is precisely H1A OA star and pick 0. So pick 0 is precisely the kernel of that. So a kernel of this map from H1 OA star to H2. So this is precisely the connecting homomorphism. So that is precisely the first Chern plus of your line bundle, which takes values in H2AZ. So the kernel is precisely going to be H1 OA modulo the image of H1AZ. So that is precisely your pick 0. So that means all those line bundles whose first Chern class is 0. So from here, what we see here is that we want to understand the line bundle. So somehow we want to again go back to the linear algebra on the lattices. So that's what one is aiming at, to understand the structure of line bundles. So you start with the, so the first point to note here is that you start with the line bundle and then you look at its image in H2AZ. So we saw in the previous slide, because we can recognize your complex torus as product of circles, we said that your H2 is all generated by the exterior powers of H1. So that is precisely saying that H2 with values in coefficients in Z is precisely the space of alternating two forms on the lattice with values in Z. So the image form is a Riemann form. So that means this alternating form satisfies certain nice properties. And now if you look at a semi-character, so a semi-character on your lattice is precisely a character up to a constant which is given by a scalar, which is e power pi I, image of whatever the Riemann form actually. So there is some indiscrepancy coming from this factor, your Riemann form here. So this is what you get. So the Appell-Humbert theorem basically says that your line, the space of line bundles, which is precisely Picard A, and so there is an exact sequence like this, and pick A to the kernel of H2AZ to H2AO. So that means you are just looking at the first Chern classes. So the image of your first Chern classes. So that is precisely the rightmost group in the second row. and the kernel is precisely pick 0. So this short exact sequence can be identified with the space of all pairs. So where psi is going to be a Riemann form together with alpha, which is a semi-character as above. And then you can map this to the first factor, which is a Riemann form. And the kernel is precisely the space of all characters. So when you say it's a character, it precisely means that you don't have the form here actually. So this is precisely the content of Appell-Humbert theorem, which recognizes the space of all line bundles with such pairs, and the pick 0 is identified with the space of all characters on your lattices. So I think this is what we discussed last time, and so let me go back to what we want to look at today. Right. So now, at least in this talk, so I want to look at these 4 topics. So very interesting topics. So I have then left many topics actually which are interesting. So previously I thought I would look at the theorem of cube and so on, theorem of square, theorem of cubes. But then I thought that that might be a bit away from the uh, theme of this meetings. So somewhere I hope that the Jacobian varieties, Riemann rock theorem, and the dual Abelian varieties might be something useful for the subsequent talks on these topics. So I would like to discuss the dual Abelian varieties and then sort of look at polarizations and invertible sheaves. So invertible sheaves are precisely line bundles. And once you define, look at line bundles, so the next most important thing is to look at Riemann-Roch theorem. And once we look at the Riemann-Roch theorem, I would like to define Jacobian varieties coming out of compact Riemann surfaces, and basically give the content of, state the content of Abel-Jacobi's theorem. So I hope to explain all these notions without proofs, of course, and but at least sort of give an idea what how these theorems work. And so there would be still many other topics actually. I mean, ideally I would have liked to look at prim varieties, prim Turin varieties, but I think that is sort of quite away from what most of you would like to look at. So I'm very sorry to Devendra. He wanted to me to look at hypergeometric, the Jacobians and so on, but unfortunately, somehow I couldn't manage to look into all those topics actually. But at least I think we will get some idea of all these topics. So Jacobian varieties, so as such we can try to look at special curves and try to understand their Jacobian varieties and so on. So basically in terms of the endomorphisms of Jacobian varieties, so that's something very interesting topic which I have left out from these 2 talks. So the endomorphism, something called as Rossetti involution, and so something more arithmetic on all these topics actually. So that I haven't really touched on. So, but maybe somebody else will look at it at some point, next couple of weeks or next couple of months, perhaps. Okay, so let me start with the dual Abelian varieties, and so let's look at those slides. Right. So the motivation to look at dual Abelian varieties comes, of course, from elliptic curves again. So you start with a smooth projective curve C. So then we denote pick 0 of C. So this is the group of isomorphism classes of divisor classes of degree 0. So there is a variety structure on your pick 0, making it an Abelian variety. So we would actually, so that is the content of Abel-Jacobi theorem. How do you recognize this space as an Abelian variety? Because anyway, I would like to look at it from the complex point of view. And so that is what would lead us to Abel-Jacobi theorem. So in general, so once you are able to define an Abelian variety corresponding to a curve C, one wants to extend this for any Abelian variety as such, and it motivates the definition of pick 0 of any Abelian variety A. So you start with an ample line bundle on A. So then there is a homomorphism from A to pick of A. So what is it? So this is precisely given by, you take any point. So okay, so this is actually over any field. So when I say that we take a point, so I essentially mean a k valued point on your Abelian variety A, and then you send it to the pullback of your line bundle under the translation map TA, and then tensor with L inverse. So both of this, your pullback under translation, that's another line bundle on your A, and then you tensor with L inverse. So this one, so this is going to be a line bundle again on A. So this is the map you would obtain from A to pick of A. So a priori, this is something set theoretic, but one can actually check that this is a homomorphism. This follows from theorem of square and so on, and that it is a morphism of varieties as such also. So now you can look at the subgroup, so which is the kernel of this map. So this map is denoted by lambda L. So that means you have fixed a line bundle L, and then any line bundle corresponds to a map from A to P. So the kernel is precisely going to be all those elements on your A, such that the pullback under the translation by element is isomorphic to L again. So that means your line bundle is left invariant under translation. So that is your kernel here, K of L. So the main fact here is that L is ample if and only if this subgroup which you get on A, so this is finite subgroup. So this is very important. So because if L is ample, so if you look at the Appell-Humbert theorem, it basically says that the Riemann form is non-degenerate. So that is what your translation looks like on the lattices in terms of your bilinear forms. So this is something very unique only for Abelian varieties. If you look at any other manifold, so you cannot characterize line bundles and ampleness in such linear algebraic terms actually. But for Abelian varieties, ampleness essentially means that the Riemann form which you get, it is actually a non-degenerate form. So it's very simple to uh, describe ampleness of line bundles in terms of this linear algebraic data. And in terms of the map from your Abelian variety A to pick of A, it precisely means that the kernel, so kernel is all those points on A, which such that the pullback under translation is of a line bundle is again isomorphic to L. So that is what is K of L. So L is ample if and only if this subgroup is finite subgroup. So this is a very useful criterion, and actually one also understands the structure of KL, and there is a Weyl form defined on this finite subgroup as well. So this is pick 0. So pick 0 is going to be, sorry, it is not pick 0 of L, it should be pick 0 of A. So this is going to be all line bundles such that this subgroup K of L is the whole group A. So that means whenever you have, if you pull back a line bundle under any element of A, it still corresponds to the same line bundle. So that means K of the kernel is your whole group. So that means this map lambda L is in fact trivial map. So that is what it means. So in that case, you are, this is what characterizes your pick 0 of an Abelian variety A. Okay. Right. So in complex geometry, so the points of pick 0A essentially parameterizes the line bundles on A whose first Chern class is 0. And so there is another way to characterize your Picard variety. So functorially, you can consider a pair A hat and a sheaf P. So where A is any algebraic variety and P is an invertible sheaf on your product A cross A dual. So why we need it functorially is because so this is sort of a moduli problem, because we want your pick 0, something like which parameterizes line bundles on A with satisfying certain properties, something like its first Chern class is 0 and so on. So whenever you are dealing with a parameter space, so essentially it means that we are going to talk about a moduli space of line bundles. So whenever you want to think of it as a moduli space, so the first thing is that moduli problems or moduli spaces are always defined functorially. So that means you can extend the base scheme as such. So there should be some moduli property which should be fulfilled. So basically we want your A to be an algebraic variety and P is an, I think it should be A hat here, sorry. A hat is an algebraic variety and P is an invertible sheaf on A cross A hat. So what is the property you require for such a sheaf P, which is a line bundle, that if you restrict on any little b on A hat, it actually corresponds to a line bundle on A, so that its first Chern class is 0. So essentially we are saying that your Poincare sheaf, your invertible sheaf P, it parameterizes degree 0 line bundles on A. So degree 0, I mean that the first Chern class is 0. So this is what it means, that your bigger P is sort of a universal object with such property. And then the second property precisely says sort of it rigidifies this property. Rigidifies in the sense that now I have several choices of P, because you can always pull back any line bundle on A hat and tensor with this P, and that will still have the same property, that if P tensor with something pulled back from A hat, if you restrict on any A cross B, it will still correspond to the same line bundle of degree 0 on A actually. But that is not what we want actually. But so we want to sort of rigidify that property. So if we say that if you restrict on A cross 0 cross A hat, a dual, so this is trivial. So the second is just rigidifying your sheaf P here. Okay. So these two properties sort of identifies or defines your moduli property. So we call A hat the dual abelian variety of A and P the Poincare sheaf if this pair A hat P, it has the following universal property. What is the universal property? That if you take any other pair T comma L consisting of a variety T and a line bundle L on your product space A cross T, such that if your line bundle, if you restrict on A cross little t, so then that corresponds to a line bundle on A whose first Chern class is 0. And then the second one is a rigidifying property. So whenever these two properties are fulfilled, so then there is a unique morphism from your variety T to A hat. So that means sort of A hat is sort of universal for such properties. And further we want that the pullback of your Poincare sheaf is isomorphic to the line bundle L you had on this product A cross T. Right? So this is sort of, so that means your P has such a universal property. So in that case, we say that A hat as a Picard variety, or it is also called as a dual abelian varieties. And another fact here is that such a variety, it commutes with extension of scalars. Because when we are talking about functoriality, so actually you can define it over any field, and then it commutes with extension of scalars. So that means essentially saying that you want to look at this functorial properties over a K, and then you extend it over a bigger field, say capital K, and or it is same as saying that you look at these functorial properties and then extend, find the Poincare sheaf over K. So either way, it is going to be the same object you would get. So this Picard variety is universal and commutes with extension of scalars. So now we want to look at polarizations and invertible sheaves. So a generalization of elliptic curve is a polarized abelian variety. So it is not just an abelian variety, but it comes with a polarization. And what is a polarization? So a polarization, you can actually think of, at least in complex geometry, it essentially means an ample line bundle, a class of an ample line bundle. So that is called as a polarization. So essentially it means that ampleness means that some power of your line bundle embeds it in some projective space. So that is what is ampleness of line bundle. So a polarization is, you can also call it, I think of it as the first Chern class of an ample line bundle. So actually, because we want to look at it over any field, so in this terminology, basically we can say that it corresponds to an isogeny from A to A hat. So why do we call it an isogeny? So what is an isogeny? So you take any map between two abelian varieties, you say it is isogeny if and only if it is surjective and it has a finite kernel. So that is what is meant by a isogeny. So I'll just repeat, and a homomorphism between two abelian varieties, which is surjective and it has finite kernel. So that is called as an isogeny. So in these terms, actually, we already described a map lambda L corresponding to a line bundle from A to pick 0, right? That is what we looked at in the previous slides. And so then we say that you look at its kernel, which was denoted by K of L. And we said that such a kernel is going to be finite if and only if that line bundle is going to be ample. So ampleness is same as polarization. So we can alternately say that whenever you have an isogeny, so then your lambda is essentially going to look like lambda L for some ample line bundle. So that is another way of saying that. So that is called as a polarization. Now, the degree of a polarization is the degree of the isogeny. So that means you have a map between two varieties. So the degree is going to be just counting the number of elements in any fiber here. So that is what is going to be your, or it is same as saying you look at the cardinality of your kernel K of L. So that is called the degree of a polarization. So when degree is 1, the polarization is said to be a principal polarization. So that is same as saying that this map A to A hat, so this is actually going to be an isomorphism. So then in that case, you would call this to be a principal polarization. So just keep this in mind, what is a principal polarization, because when A is replaced by a Jacobian of a variety, so then a Jacobian of a variety comes equipped with a theta divisor, and that is actually, and you can look at the line bundle associated to a theta divisor, and that will correspond to a map from your Jacobian to its dual of your Jacobian, and that is actually going to be an isomorphism. Okay, so this is something very special for Jacobians, and that's why we say that your Jacobian varieties comes equipped with the principal polarizations. So whenever actually there is a, you look at the moduli space of curves of a fixed genus, so there is a Torelli map which on your moduli space. So it takes, so it associates to a Jacobian of a variety to it associates to curve, a smooth projective curve, to its Jacobian variety together with its principal polarization, theta or O of theta, whichever way you like. So it corresponds to a map from your moduli space of curves to the moduli space of principally polarized abelian varieties of genus or dimension G. Okay, so that is your classical Torelli map. So that is, so it's important to know what is the meaning of principal polarization. So it just means that your abelian variety is isomorphic to its dual abelian variety, and the map is precisely given by an ample line bundle. Okay. So this is what it means. And
So how much the theory of the elliptic curves extend over these type of varieties?
sorry, say it again.
How much the theory of the elliptic curve extend over this generalization polarized abelian variety?
Yeah, so you can also take an elliptic curve and take its dual, because see, on an elliptic curve, you can just choose a single point, and that is actually an ample, that corresponds to an ample line bundle, right? You can take O of some little p if you like, and that corresponds to map from your E to its E dual, and that is going to be an isomorphism. Because on a curve, you take O of any point. So that is all. That is always an ample line bundle, because you can always take a large multiple, say something like O power 2g plus 1. That is always going to be very ample. So O of a single point is always an ample line bundle, and that will correspond to an isogeny from which is actually an isomorphism from E to E dual. Right? So this is what one is trying to extend to higher dimensional abelian varieties. But the thing is that if you are going to look at abelian varieties, not all abelian varieties comes equipped with the principal polarization. Okay, so only those abelian varieties which come with the principal polarization, that only you can identify sort of with elliptic curves. In the sense that you can also look at product of elliptic curves, and then on each single component you can have this O of a P. So that is an ample line bundle. So you can look at the tensor product of all those ample line bundles coming from each factor, and that is corresponding to a principal polarization on a product of elliptic curves. So actually, if you look at the space, moduli space of abelian varieties with principal polarization, so there will be a closed sub variety in that moduli space, which parameterizes product of elliptic curves with principal polarization. So that way you can think of the role played by elliptic curves here. Okay.
I see. Thanks.
Right. See, elliptic curves, they are very simple, because any point correspond on your elliptic curve, it corresponds to an ample line bundle. It is a principal polarization. And on the curves, actually, we can, the line bundles are characterized by the divisors, and you can play with the degree of divisors, and that completely characterizes your study of line bundle set. But when you are going to look at higher dimension, the degree of a line bundle is not defined. All you can say is to look at the first Chern class, and that is not a number, but that is actually something lying in your second cohomology group of your manifold with values in Z. So it is no longer a number. So that's the first difference. But for abelian varieties, at least we can identify it, that space with the alternating two forms on your lattices. So in that sense, we don't get a number, but at least we capture a bilinear form. So that's what this whole study amounts to. Okay. Any question? Yeah, please ask.
Yeah, thanks.
Okay. So the whole point is that you have plenty of abelian varieties which do not have principal polarizations. I mean, they do have polarizations, but they need not be principal. That means if you look at this map from that abelian variety to its dual abelian variety given by lambda L corresponding to some line bundle, it may always have some kernel actually. It is not true that always the kernel is going to be trivial. So you have abelian varieties which don't have principal polarizations. But now actually what you, for example, a quick example could be to take, because I just said that you take the Jacobian of a curve, I said that there is a classical theta divisor and which is a principal polarization. And so you can take some finite covering of your Jacobians actually, because if you take finite coverings, say ethyl coverings, one can also always construct such coverings. They are again going to be abelian varieties, but they are not going to be principally polarized, because if you pull back the line bundle from below, so it will attain more sections and it is not principally polarized. So you can always construct abelian varieties which are not principally polarized. Okay, so that's so you get plenty of such non-principally polarized abelian varieties. Okay, so Zarian stick is important in the sense that whenever you have a non-principally polarized abelian variety, you can construct a principally polarized variety out of it, in the sense that you take A cross A dual and take the four copies of that. So that means you just take four product of such a double product, and then that is always principally polarized. So that is useful actually, and in the sense that over finite fields and so on, people try to understand how many abelian varieties are defined over a finite field, and in such counting problems, it is useful to know have such a theorem. So this is something due to Zerhin. Okay, so the next I want to understand, I want to describe is the Riemann-Roch theorem. Because on a curve, so what does the Riemann-Roch theorem does? So on a curve, what it says is that you can compute the Euler characteristic of your line bundle on a curve with the dimension of your cohomologies of your line bundle. So something like if you take a Riemann-Roch theorem on a curve, so it basically says that H0 of a line bundle minus H1 of L. So this is same as degree minus genus plus 1. Right? So this is your classical Riemann-Roch theorem on a curve, degree minus genus plus 1. So that means this number, Euler characteristic. So similar numbers we want to compute for an abelian variety. That if you take this alternating sum of the cohomology of a line bundle on your abelian variety, which is the chi of L. So what is it actually? So it basically says that if a line bundle looks like L of D, so then it is going to look like your Euler characteristic is the self-intersection number d power g modulo g factorial. Right? So this is something you can also say it for elliptic curve, because
the Euler characteristic you need the alternating sum.
Right, alternating sum. Even for alternating sum actually. Yeah, I forgot actually. There should be a sum missing here. Right. Thank you. Yeah. So it is the alternating sum. So actually you can, so this is something you can use this self-intersection number you would recognize on an elliptic curve. So what does it say on an elliptic curve? So this is basically saying that H0 of a line bundle, H0 minus H1. So this is same as degree minus genus plus 1, right? So but H1 is going to be 0 for on an elliptic curve because the canonical class is trivial. So your H1 is recognized as H0 of K minus L. So K is trivial, so H1 is 0. So it basically says that H0 of L is same as degree minus genus, so that is 1 modulo 1 degree. So this is what one can is generalized to higher dimensional case. So as professor mentioned, so there is a sum here, alternating sum for the Euler characteristic. And so this is in higher dimension also you can write your Euler characteristic as this self-intersection number d power g modulo g factorial. So this has a very nice looking shape actually, and this has lot of applications. And right. So one application I can say here is that if you look at yeah, so what it basically says here is that if your line bundle is ample, so only one cohomology is non-zero and the rest of them are all zero. This is also some fact. So basically, whenever your line bundle is ample, this chi of L corresponds to, and if suppose it has sections, it corresponds to only H0 of your line bundle. All the other cohomologies are going to be zero. So this is again something very special on abelian varieties. That if your dimension KL is 0, then your Rth cohomology is non-zero for exactly one integer. And if it is ample, so dimension of KL is 0. So dimension is saying that it is finite. So once it is finite, it essentially means that your line bundle is ample. And in that case, you have, and if it is very ample, this is non-zero and rest of the cohomologies are 0. So this term or this equation basically helps us to compute the dimension of space of sections of a very ample line bundle on an abelian variety in terms of the self-intersection number of your divisor and modulo this factorial, g factorial. Okay, so this is a useful equation and it helps us to characterize line bundles also. Because this self-intersection, because as we said that by Appell-Humbert theorem, we can look at, express your first term class in terms of a bilinear form, which is Q symmetric. and then actually we can actually get a nice shape for the matrix of your form, skew symmetric form. And so you have only some numbers, something like D1, D2, DG in the upper diagonal. And so you can just take the product of those D1, D2, DG, and that is precisely going to be the Euler characteristic. So one can actually express the dimension of space of sections as something coming from that matrix form of your skew symmetric form. Okay, so now let us look at the last topic, which is the Abel-Jacobi theorem. So you start with the smooth projective the projective curve here, sorry, not variety, over complex numbers. That is, C is a compact Riemann surface. So now the first theorem, what we have is that there is an embedding of your first cohomology of your curve C with coefficients in Z inside this dual of the space of holomorphic forms on your curve C or your compact Riemann surface C. So what is this embedding? So here you take any cycle, say call it to be a one cycle, which is denoted by gamma, and then this gamma is corresponds to a linear function.
Smooth projective curve over C, right?
Yeah, curve actually. Yeah. Some typos are there actually. Yeah.
Curve
Correct.
over C.
Correct. So C is a variety, compact Riemann surface. So the first theorem I want to explain is that so there is an embedding on the one cycles on your curve inside the space of linear forms on the space of holomorphic forms. So what is this embedding? You start with any uh, one cycle, call it gamma, and then it corresponds to a linear functional on the space of holomorphic forms. So this is just saying you take some holomorphic form on your C and integrate it along your cycle gamma. So this is the linear function you get. And the theorem says that this is in fact an embedding. So you can consider the quotient of this vector space modulo the group of cycles here. So now because C is of say genus G, so this vector space is a complex vector space of genus G, and then you are going modulo the group of cycles. So this is H1 is essentially a free abelian group on 2G generators precisely given by the loops. So C is of genus G essentially means that it is G holes. So each hole will give rise to two cycles. One is something winding along the circumference and one winds along the inside loop here. So you have 2G number of generators, and so that corresponds to a lattice inside your complex G dimensional space here. So let us denote it by Jacobian, say Jac C. So at least we have gotten hold of a complex torus in this case. And then we want to say that such a complex torus, we want to identify it with something known actually. So that means as a group variety as such. So this is of course a complex torus, so it has a group structure. And then we want to say that there is some kind of a variety structure as well here, projective variety structure. So the first theorem, the classical theorem, is due to Abel. So it says that you start with any divisor D of degree 0 on your curve. So you can express it as you look at the zeros and sum of the zeros, and you subtract with the number of poles, and it is degree 0. So you can the I runs from the same numbers. You have same number of P's and same number of Q's. And now you pick any other point P on C. So then there is a meromorphic form on F on C whose zeros are precisely Pi's and whose poles are exactly at Qi. So if and only if for any paths gamma I from P to Pi and gamma I prime from P to Qi, so there is an element gamma which is a cycle such that this linear form is precisely given by uh, the linear functional given which is integration along gamma. So that is same as saying that forget this omega. So what this saying, what we are trying to say here, or what Abel's theorem says is that you pick a divisor of degree 0. So, and you pick some reference point P, and corresponding to a reference point, you can construct some paths gamma I corresponding to zeros. And then you can construct, look at any other paths corresponding to your poles Qi, which joins with this reference point P. And then you take so you get two linear functionals, integration along these paths, gamma I. And then the other linear functional is precisely integration of forms along your paths corresponding to the poles here. And take its difference. So this is precisely the linear function corresponding to a cycle gamma. So there is something. So this is same as saying that your, how to say, and this is true if and only if this divisor corresponds to a meromorphic function. So this is same as saying that you, this degree, so this is, how do you say, the principal divisors, right? So the principal divisors precisely corresponds to the space of cycles, right? Because when we look at this quotient of your, which is given, which describes your Jacobian, so you have H1CZ. So this H1CZ, so which we have recognized it as some space of giving linear functionals on your space of forms. So this H1CZ, you can think of it as precisely the space of principal divisors on your curve. So that is what is Abel's theorem. Okay. And what is Jacobi's theorem? So Jacobi's theorem says that you start with the linear functional on your space of forms. So then you can, there exist some G points and paths such that any such linear functional is precisely given by integration along such paths. So this is Jacobi's theorem. So this is something not very clear. I mean, like, okay, so there is Griffith's intermediate Jacobian and all, which also works on the same principle. And so on a curve, it precisely says that any linear functional on the space of forms corresponds to the integration along paths corresponding to some G number of points and for some reference point P. So altogether, this Abel's theorem and Jacobi's theorem, so what they precisely imply is that you consider a map from the space of divisors of degree 0 to your Jacobian. So there is some gamma I. So what it says is that, so any divisor of degree 0, you write it as sum of Ni Pi, and it corresponds to a linear function. So this is, and some Ni is there. Yeah, some typos are there. Actually, I'll just make these corrections when I send the file. So you look at the linear functional, which is integration along these gamma I. So there is a sum and Ni here. So such a thing. So this is going to be surjective. So that is what is the Jacobi's theorem, that this map given by integration along paths. So this is surjective. And also what it says is that this map is injective modulo principal divisors. So because the principal divisors are something which go to 0 here. So that's what it says. Okay. So together with Abel's theorem and Jacobi's theorem says that this is precisely an isomorphism. That from peak 0 is isomorphic to the Jacobian. Okay. So this is something very classical, and so I want to say that, okay, so this theory of Jacobians is very interesting. I've just touched the statements, nothing more here. But actually one can similarly define Abel prim map. So that means that is very interesting and a hot topic in algebraic geometry. So why all this is important, like looking at prim varieties or prim Turin varieties, is because, as I mentioned, that we do have associating a curve associating a Jacobian to its curve basically corresponds to a morphism from the moduli space of curves of genus G to the moduli space of principally polarized abelian varieties of genus G. So you do get a map between two such moduli spaces. And we also know the dimension of these moduli spaces. So if you fix the dimension of your abelian variety to be G, so you are just going to look at the morphisms from Mg, which is the moduli space of curves of genus G. And so the moduli space of curves of genus G, it has dimension 3G minus 3. And if you look at the moduli space of principally polarized abelian varieties of dimension G, that is dimension D, G times G plus 1 modulo 2. So as soon as G is bigger than 3, so this map is not an isomorphism. So then we see that the numbers are different, and G times G plus 1 over 2, the dimension becomes larger than the dimension of your moduli space. So immediately we see that this morphism is not surjective actually whenever G is bigger than 3. So in that case, people started asking, so at least in dimension 2 and dimension 3, we can recognize the principally polarized abelian varieties in terms of curves. So that means in terms of curve theory, you start with an abelian variety in dimension 2 or 3. It is always going to uh, be isomorphic to a Jacobian of some curve. And we know that those are say finite, that's a finite map. So you always can recognize it as a Jacobian of a curve. But when if you look at a principally polarized abelian variety of dimension 4, it is no longer true that if you take some generic point in that moduli space of abelian varieties, that is no longer going to look like Jacobian of a curve. There will be a loci, which is actually given by a divisor in dimension 4, which corresponds to Jacobian loci actually, whose points correspond to Jacobian of a variety of a curve. But actually, if you consider a generic point in the moduli space of abelian 4 folds, principally polarized 4 folds, a generic point in that moduli space is no longer Jacobian of a curve. So then people said, okay, is there a way it can still be related to curve theory? And the point here is that yes, indeed it is true. And that precisely is what they said, that any generic point in that means generic abelian 4-fold is going to look like your prim variety associated to a double cover. So whenever you have a double two-sheeted covering of two curves, say C prime to C, so then it corresponds to a reverse map on your Jacobians. So basically, because Jacobians, we recognize it as a variety parameterizing line bundles of degree 0 on your curve. So you take any line bundle on your base curve and pull it up on your top curve, and so that is still a line bundle of degree 0. So you can say that if you take, for example, it's an Appell curve of a two-sheeted Appell curve. So it corresponds to a map from the Jacobian of your base curve to the Jacobian of your top curve. But now you can see that by Riemann-Roch formula, or rather Riemann-Hurwitz formula, you can compute the genus of your base curve and the genus of the top curve. So those are going to be different. So something, if the base curve has genus G, then the top curve has genus, I think 2G minus 1 by Riemann-Hurwitz formula. So if you look at the reverse map on your Jacobians, that means Jacobian of your curve C to Jacobian of your top curve C prime. So then it is only going to so the image is going to be a sub-abelian variety of your Jacobian of your top curve. And so actually one can, so basically we are dealing with complex tori. So your top Jacobian, it splits into two abelian subvarieties. So the complementary abelian subvariety is what is called as a prim variety. So if your base Jacobian has genus G, so you get a G dimensional abelian subvariety of your 2G minus 1 dimensional Jacobian. And so the complementary abelian subvariety is going to be of dimension G minus 1. So if you look at the moduli space of double covers, say Appell double covers, so you will take any point in your moduli space of double covers, then you can actually get a morphism to the moduli space of abelian varieties. which is of dimension G minus 1. So that is called as the Abel prim map. And people have studied, I think someone like Ron Donaghy and many others, like what is this map actually, and is it finite map, and so on. So actually the main content here is that if you look at, since I just mentioned that any uh, up to genus dimension 3, any abelian variety of dimension 3 is Jacobian of a curve, is isomorphic to Jacobian of some curve. But now if you take an abelian fourfold with principal polarization, what it says is that a generic one is not Jacobian, but it is actually a prim corresponding to a double cover, two-sheeted covering. So that means it is basically a two-sheeted covering of a genus 5 curve. So that you get G minus 1 is 4. So this is true for abelian fourfolds and abelian fivefolds. So in that sense, you look at moduli space of any abelian fourfolds or abelian fivefolds, they are also constructed from curve theory. That is another way of saying this. So this is a very rich topic, and now people have trying to understand abelian six folds. Is there a way to recognize your abelian six folds in terms of curve theory, like something like it's two sheeted or three sheeted coverings and so on. So that has been the motivation to study curves and its coverings and their coverings, and recognize the complementary abelian subvarieties, which are also called as prim Turin varieties. And actually, if you look at not just double covers, but higher degree curves, so you will have some group acting on them. So it's not just one single abelian complementary subvariety, but according to the characters on the group, you would have several such many sub complementary abelian subvarieties. So people are trying to understand if they are principally polarized or not, and so on. So, so with this, actually, my time is up. So I'll stop. So I invite questions from you. So I'm sorry, there are some typos actually, which I promised to correct them and send the file.
Thanks, Professor.
Can you explain this Abel-Jacobi theorem for elliptic curve?
Yes. So Abel-Jacobi map. So basically on an elliptic curve, so E is isomorphic.
So for elliptic curve, there is this pay and pay prime.
Right.
So you are saying something about these functions, I guess.
Right. So I think that is actually clear, because elliptic curve, it basically says that E is isomorphic to its dual. It's Jacobian itself actually. We don't get anything new there.
Yeah.
They are isomorphic. Yeah, E is isomorphic to its dual. Jacobian is itself for elliptic curve.
Yes. So Abel-Jacobi theorem doesn't say anything.
So it just says that is, you can still look at, see, because your canonical class is trivial there for an elliptic.
Yeah.
So it is only one dimensional space you get. Right? So this is H0 C omega C, it is one dimensional space. And then basically you are saying that this one dimensional space is precisely given by whatever it is here.
So if there is a divisor P minus Q,
right,
there's 2 points.
right,
So given any 2 points on the elliptic curve, then
right,
there is symmetry and you can translate and so on.
right.
But then there is some meromorphic function which can be expressed in terms of pay and pay prime,
Right.
which has that divisor.
Right. So basically it says that you take right. So any such divisor of degree 0, so it will correspond to meromorphic function if and only if it corresponds to this cycle. So you have elliptical, you have only 2 generators, which is one winding along your hole, one winding the other side.
Right.
And any such path actually will correspond to, if and only if it is homologous to one of them. And so then it will correspond to a meromorphic function. That's what it says.
So what does this condition satisfied means in terms of that rational function between P and P prime and having that those zeros and poles? Is that some classical theorem there, or maybe it's
Yeah, I think Abel's theorem itself is classical. So I don't know.
No. But I mean,
something you want a simpler term to that.
no,
Yeah.
whether one can say that in terms of the functions P and P prime. So you know the zeros of P and P prime. And so many rational functions, something. I don't know. Yeah. Yeah, very good. So very clear.
Yeah, sorry,
Yeah.
some typos are there. Something I have to clear it.
That's it.
So
Good survey of the whole field.
yeah.
Yeah, I just touched the topics actually. I think there is still much. I think the short key problem is very
Yes.
important actually for the model of Abelian varieties.
Yeah.
So all this actually sort of motivates that problem. How do you characterize Jacobians on a model of Abelian varieties?
Yes.
So some brief introduction.
Okay, Professor, thanks again
Yeah.
for this wonderful course on the Abelian varieties in 2 talks.
Yeah, thank you very much, Devendra. Yeah. Thanks for listening.